Welcome to qnawire.
So for a complete inelastic collision, the linear momentum is conserved. So for the first part, we apply conservation of linear momentum, which means that the initial linear momentum is equal to final linear momentum. So doing that, we get this equation. So mb times v naught is the initial linear momentum, and finally we have both the masses, the total mass, which is mb, mass of the beam plus mass of the man, times the final velocity. Now from this equation we can find the final velocity, and using the values listed for mass and initial velocity, we calculate the final velocity to be 14 meter per second. Now, for the second part, the angular momentum about the center of the mass is conserved. So this equation we will use. But before that, we find the center of mass relative to the center of the rod, relative to this black dot, and we take positive y-axis to be downward. Now, doing that, we find the center of mass. So this is the equation that we will use. So y center of mass is the uh, summation of the mass times radius of each of the components over the total mass. So we have mb times rb plus mm times rm over mb plus mm. So b basically means beam and m stands for mass. Now rb is 0 because it's at the center. So now we have mm times rm, and rm is basically L over 2, and in the denominator we have mb plus mm. So we do the calculation using the values listed over here and find the center of mass to be equal to 0.2975 meter below the center of mass of the rod. So this distance over here is the center of mass of the rod plus man. And this is the position of the center of mass of the rod plus man. And this is the distance, 0.2975 is the distance between both the center of masses. So we denote this value right here to be RB. Let me just write it over here so that we have all the values listed at one place. Remember that this distance is the distance of the center of mass of the rod plus man system. So rod plus man system from the center of the rod, center of mass of the rod, I'm sorry. So let me just reframe my sentence. So RB is the distance between the center of masses of the rod and the rod plus man system. Now we proceed to find the moment of inertia of the beam about the center of mass of this entire system. So we have the center of the beam, which is 1 over 12 mb times L square plus mb square rb square. So this is the moment of inertia of the beam. And for moment of inertia of the man, we should have mass times the radius, the square of the radius of the man. And here the radius is half L minus rb square. Now we apply conservation of angular momentum. Okay, so one thing I missed out is if you are worrying about how to get this moment of inertia, so we have used parallel axis theorem for that. So if you don't know what parallel axis theorem is, please take a look into the textbook, and it's really simple and I'm sure you'll figure it out. So that is what we used here. Second, we apply conservation of angular momentum. So we have the initial angular momentum to be mass times initial velocity times radius of the beam. And for the final angular momentum, we use the other formula, which is I times omega. And I here is the total moment of inertia, which means the moment of inertia of the beam plus mass times the final angular velocity, which we want to find. So doing that, we find an expression for omega f. The next thing we do is find IB using the values that are listed here. So basically all of them, all the values that you need are listed over here. And for the, and you do the same to find the moment of inertia of the man using the values over here. And after calculating IB and IM, plug them over here and plug the mass of the beam, the initial velocity R, and RB that we just calculated, that's already written over here. Plug that as well, and you find omega F to be equal to 5.307 radian per second. So this is the final angular velocity when the man is included in the rod.